sometimes when events happen sequentially, like a first event, a second, a third, and so on, we can use a tree diagram to find particular probabilities. Here's an example. Okay, I'm going to read this through. So imagine that there's a factory, and in this factory there's 3 machines, and they produce face masks. Machine A produces 55% of all the masks, but has a 5% defective rate. Machine B produces 25% of all the masks, but has a 6% defective rate. And then machine C produces 20% of the masks and has a 3% defective rate. So imagine now you just pick a mask at random and it's found to be defective. So you pick a mask at random and you see that it's defective. What is the probability that that mask came from machine C? So we'll start with the tree here. I'm going to start over here with a node for the base of the tree. Now I've got 3 machines, machine A, machine B, machine C. So let's label these. This will be machine A, machine B, and machine C. And machine A produces 55%, so I'm going to put that probability right here. So up that branch, there's a 55% chance of moving up this branch. And then for branch B, that's what? 25%. So this is going to be 0.25 here. So there's a 25% chance of moving along this branch. And then for C, we've got a 20% chance. And I think those should add up to 100. Let's just check. 55 and 25 is 80, 100. Okay, so we've got a good distribution here. Now, let's travel up machine A. Suppose we're at machine A. Well, what can happen with machine A? Well, machine A could produce defectives or non-defectives. Now, machine A produces 5% defectives, so this would be 0.05 and this would be 0.95, right? They have to add up to 1, so 5% defective means 95% non-defective. No, maybe I can write that non-defective a little bit clearer. Non-defective. In fact, I'm going to get it out of the way. Non-defective. Now for B, let's look at mask B. Mask B, well, that could be defective or, right, defective or non-defective, and 6% are defective. So 6% defective, then 94% are non-defectives. And for C, machine C could be producing defectives or non-defectives, and they let's see, what is that? That's 3%. So 3% defectives, and that must be 97% non-defective. So here's what we're looking for, right? We're looking for this down here. What's the probability that it came from machine C? All right, so what's the probability that we get machine C given that it's defective? Right, I'm going to write down what I'm looking for. I want the probability, oh, we don't need that color. I want the probability that it's machine C given that it's defective. Well, this is a conditional probability problem. We have a formula for this. It goes like this. You intersect them on the top, the probability of machine C and defective, divided by the probability of the event that's given, right? This one right here. So we can find these probabilities just by looking at our tree diagram. So look at the numerator. This is the probability of C and D. So probability of machine C and D. Now just follow it down here. Here's machine C and D. All right, so how do you get here? This one and this one. So it's 0.20 and times 0.03. So our numerator is going to be 0.20 times 0.03 divided by. Now the denominator is defective. So how do you get a defective? Well, look over here. Here's how you can get a defective. You could get it here, here, or here. I'm going to make a note of that. I could get it here, here, or here. Now, how do you get this one here? Well, this one comes from going to A and times to defective. So this one here is going to be the 0.55 times 0.05, or, now or is a plus, right? And is a times, or is a plus. I could get it from here, that's the first one, or I could get it down here. Now to get here, I have to go through these branches. 0.25 and 0.06, and is the times. So this is going to be 0.25 times 0.06, or plus, I could get that D right here. Now to get here, I have to come down to C, this branch, and D. So it's 0.20 and times 0.03. So it's 0.20 times 0.03. All right. Now look, every time you do this, one of these denominators, one of the terms in the denominators is going to match the numerator. Right? It happens to be the third one this time. That will always happen. One term in the denominator will always match the term in the numerator. But we know we can't cancel, right? Because you can't cancel common terms. If terms are separated by plus or minus, you can't cancel. So these do not cancel. So now all we have to do is just compute. So when I did that, I came out with this number right here. I got 0.12371 ... But probability, I'm going to round this to 4 decimal places. So I'm going to say this. The probability that we got that this mask came from machine C, given that it's defective, is 0.1237. Now, if I wanted to get a kind of interpretation of this, what if I just rounded off to 2 places? If I just rounded off to 2 places, I'd have 0.12, which is about, what, 12%? So what that tells me is that if we just randomly select a mask and find it to be defective, there's about 12% chance that that defective mask came from machine C.